Welcome to the Explainer. So, have you ever looked at a massive data set comparing different groups? Maybe it's different medical treatments or, agricultural fertilizers, and wondered how researchers actually draw firm, scientifically sound conclusions from all that data? I mean, if you're just comparing two groups, it's relatively straightforward. But what happens when you have three, four, or even 10 groups? How do we figure out if there's a real tangible difference between them without descending into absolute statistical chaos? Well, today we're demystifying a true powerhouse statistical tool called analysis of variance, which is commonly known as ANOVA. It is absolutely the gold standard for separating the signal from the noise when you're dealing with multiple groups. Here's a quick roadmap for this explainer. We'll kick things off by introducing analysis of variance. Then we'll walk through a super intuitive dog show example. After that, we'll look at how the math actually works, cover the key rules and assumptions, and finally, wrap up with the different types of ANOVA. All right, Section 1, Introducing Analysis of Variance Beyond the T-Test. Okay, let's dive into this. For decades, if you wanted to compare the averages of two groups, you just use a standard t-test. But in complex research, honestly, that's incredibly restrictive. We really needed a better tool. Enter analysis of variance, or ANOVA. It's essentially a family of statistical methods used to compare the means of two or more groups. And it does this through a pretty brilliant trick. It analyzes the variation between the group means and compares it to the variation within each group. Think about it like this. If the variation between your groups is substantially larger than the random variation bubbling around within each group, it strongly suggests that the group means are actually truly different. The development of this tool was a centuries-long journey. The groundwork started way back in the 1770s when Pierre-Simon Laplace was performing some of the earliest hypothesis testing. Then, around 1800, Laplace and Carl Friedrich Gauss developed the least squares method, primarily for astronomy. But modern ANOVA, as we know it today, that was championed by the legendary statistician Ronald Fisher. In 1918, Fisher introduced the formal term variance while studying genetics, and by 1921 and 1923, he was practically applying ANOVA to agricultural data, literally dividing up the variation in crop yields across different plots subjected to different fertilizer treatments. Fisher basically gave us the modern framework we still rely on today. Moving on to Section 2, the dog show example, understanding groupings. Before we get bogged down in the math, we really need to intuitively grasp what variance actually feels like. So let's use a metaphorical anchor, a dog show. Imagine we're at a prestigious dog show. It isn't just a random sampling of dogs, it's strictly limited to purebred, exemplary adults. Now, if you plotted the weights of all these dogs on a single graph, the overall distribution would be really complicated and extremely wide. So I have a question for you. How would you accurately predict a dog's weight based on a set of its characteristics? Essentially, how do we divide this complex, messy overall distribution into homogeneous, meaningful groups that actually explain the differences in weight? And this brilliantly illustrates the core concept of ANOVA. If we group the dogs by age and hair length, say young, short-haired dogs versus old, long-haired dogs, we get a really poor fit. The variance of weight within these groups is still massive, and the average weights between the groups end up being very similar. Basically, knowing a dog is young and short-haired doesn't help you predict its weight at all. But if we group them by breed, say Chihuahuas versus St. Bernards, we get a very good fit. All Chihuahuas are light, and all St. Bernards are heavy. The variance within the Chihuahua group is tiny, and the mean weight is incredibly distinct from the St. Bernard group. A successful grouping minimizes internal variance while proving the groups are fundamentally distinct, and that is exactly what ANOVA is measuring. Which brings us to Section 3, how the math actually works, partitioning variance. Now that we have that dog show intuition locked in, let's look under the hood and see how this translates into actual statistical formulas. The fundamental technique of ANOVA is partitioning, or splitting up, the total sum of squares. Sum of squares is really just the statistical way we measure variance. This incredibly clean equation shows that the total variance in our data simply equals the error variance plus the treatment variance. Let's apply this back to our dogs. The total is the weight variation of all the dogs combined. The error is the natural variation within a specific breed, like the slight natural weight differences between two individual Chihuahuas. We call it error, but honestly, it just means unexplained natural noise. Finally, the treatment is the actual effect of being a specific breed. ANOVA elegantly separates that background noise from the actual effect. To actually use that partition data to get a result, we rely on something called the F-test, named in honor of Ronald Fisher. The F-test creates a super simple ratio. It takes the variance between our treatments, so the breeds, and divides it by the variance within our treatments, that natural noise we just talked about. Now, what's really interesting about this is the secret trick of the ratio itself. If this F ratio is exactly 1, there is essentially no treatment effect. But as the F value increases significantly above 1, the evidence becomes incredibly strong that your treatment or your grouping actually had a real measurable effect. You then just check this against a critical value to determine your statistical significance. Next up, Section 4, Key Rules and Assumptions, the Golden Rules. As we know, statistical tools are incredibly powerful, but they only work properly if the underlying data behaves according to some specific rules. Whenever you run a standard textbook ANOVA using a normal linear model, you are relying on 3 absolute essential assumptions. First, independence of observations, meaning one data point shouldn't artificially influence another. Second, normality. The residuals, or the errors, need to follow a normal distribution. And third, homoscedasticity, which is just a really fancy word for the equality of variances. This simply means the variance of data in each group should be roughly the same. Tying it back to our dog show, for the math to work perfectly, the natural weight variation within the Chihuahua group should be relatively equal to the natural weight variation within the St. Bernard group. So the crucial point is that while those assumptions sound incredibly strict, you really shouldn't panic if your data isn't absolutely flawless. As this quote highlights, the ANOVA F-test is widely recommended because of its incredible robustness. Even if your data departs moderately from a perfect normal distribution, or maybe your variances aren't perfectly equal, especially if your sample sizes are balanced, the ANOVA F-test holds up exceptionally well in practice. It does a fantastic job of minimizing false negatives while simultaneously protecting you against false positives. Finally, Section 5, Different Types of ANOVA, Real-World Applications. Let's move to and see how this builds into more sophisticated real-world models. The one-way ANOVA is what we've mostly been discussing today, testing a single factor across independent groups, much like Fisher testing different levels of fertilizer on his crop yields. But then we have factorial ANOVA, which is super cool because it tests multiple factors at once. Instead of just looking at dog breed, a factorial design could test age and hair length together to uncover hidden interactions between those variables. And finally, repeated measures ANOVA. This is used when you test the exact same subjects multiple times, like a longitudinal study tracking the blood pressure of specific patients taking a new medicine over, say, 6 months. Whether you're studying crop yields, analyzing breakthrough medical trials, or just trying to predict the weight of a show dog, analysis of variance is the definitive tool for making sense of complex groups. It literally takes a messy world and neatly partitions it into recognizable, actionable patterns. So now that you know how to mathematically separate the signal from the noise, what complex patterns in the world around you will you decode using ANOVA? Thank you so much for joining me for this explainer, and happy analyzing.